Hello and welcome to the third video in my series on waves. This one's going to focus on light and sound waves. By the end of this video you should be able to state the speed of sound in air, state the speed of light in air, give some everyday examples that demonstrate that the speed of light is faster than the speed of sound. You should be able to use d equals v times t to solve some wave problems. And you should be able to describe an experiment that measures the speed of sound. So what is the speed of sound? The speed of sound is 340 meters per second in air. But the speed of sound varies depending on the air temperature and the air pressure. So it's different at altitude, for example, than it is at sea level. It also varies depending on the material that it's passing through. The 340 meters per second is in air, but a lot of that's to do with the density of the material that it's passing through. Sound travels quicker through more dense materials. So for example, it's 1,500 meters per second in water. It's even faster in more dense materials like steel, for example. At the beginning of the National 5 exam paper, you'll see this table here. It gives a list of the speed of sound in a variety of materials. The speed of light is much faster. It travels at 300 million meters per second, or 3 times 10 to the power of 8 meters per second in air or in a vacuum. Again, the speed of light is different in all sorts of materials, although the speed of light is fastest when going through a vacuum or through air. It's always slower when it's passing through any other material. The 3 times 10 to the power of 8 meters per second is a sort of universal speed limit. Things with mass can't get as fast as the speed of light. But if we take the example here of the two people, they're separated by a very short distance. Now light's so fast that we can pretty much say that it covers that short distance in an instantaneous time. In reality, with light being of a finite speed, then it will take a fraction of a second for the light to leave the woman and to reach the man's eyes. What this means is that you never really see anything as it is just now. Whenever you look at anything, you're looking at it in the past. It's just that for very short distances, it's maybe only nanoseconds in the past. So to all intents and purposes, it's instant over a short distance. However, over longer distances, it becomes more pronounced. The sun's about 93 million miles away from the Earth. This means that light takes about 8 minutes to reach your eyes from the sun. This means that you don't see the sun as it is just now, you see it as it was 8 minutes ago. It becomes even more pronounced over astronomical distances. If you take our galaxy, which is about 100,000 light years from one side to the other, then light that's travelling from one side to the other will take 100,000 years to reach. So we don't see things on the other side of the galaxy as they are today. We see them as they were 100,000 years ago. When we look at the universe on a larger scale, and we see the most distant objects in the universe, we see them much further back in time because it's taken the light sometimes billions of years to reach us. There are everyday examples too that show that light is much faster than the speed of sound. Thunder and lightning, for example, are produced at the same time, but you see the flash of lightning almost instantaneously because the light hits your eyes so quickly. It's only a few seconds later that you will hear the thunder begin to catch up. There are other examples as well, like fireworks, where you see the flash of the fireworks before you hear the bang. The distance of an event can be estimated then, because if we know the speed of sound and we time how long it takes for the sound to reach us, we can use distance equals speed times time to estimate the distance, or d equals v times t as we write it in physics. Here's a typical example. A flash of lightning is seen and the thunder can be heard 4.5 seconds later. So how far away was the lightning? Pause the video if you want just now and try and calculate it. Well, if the flash of lightning is seen and we can assume that the light reaches us pretty much instantly, then it's the sound that takes the 4.5 seconds to reach us later. So we could estimate the distance as the speed times the time. In this case, it's the speed of sound that we're going to be using, the speed of sound in air, which is 340 meters per second, multiplied by the 4.5 seconds, gives us 1,530 meters away. Another example is here. The parking sensor here is emitting ultrasound. Now, ultrasound is just sound waves, but beyond a frequency that's audible to the human range of hearing. So it tells you that the sound is emitted from the back of the car, reflects from the wall and back to the car, and it does this in a time of 2 times 10 to the minus 3 seconds, or 2 milliseconds. It asks you to calculate the distance between the object and the rear of the car. Again, feel free to pause the video and calculate. But we can use d equals v times t, distance equals speed times time. Again, we're just using the speed of sound, and the time is 2 times 10 to the negative 3 seconds. This will give us 0.68 meters. However, it's important to realise that that is the time from the car to the wall and then to echo back to the car. So the distance is really half of that distance, or 0.34 meters. Lastly, we're going to have a wee look at how to measure the speed of sound from an experiment. For this experiment, you need 2 microphones, both of them connected up to a timer and separated by a known distance. Something like 1 metre is fine. Measure it with a metre stick. You also need a sound to be made somewhere beside microphone 1. The sound will travel to microphone 1, and this will indicate to the timer to start timing. The sound doesn't stop at microphone 1, it moves on to microphone 2, which tells the timer to stop timing. We now have a distance between the 2 microphones and the time for the sound to travel from microphone 1 to microphone 2. It's better to repeat this experiment. Repeating experiments allows us to get more reliable results. If we repeat the experiment and get multiple times, and then take an average of those times, we might get something like this, where a distance of 1 metre is covered in 0.0033 seconds. Again using dVt, but rearranging for the speed, we get v equals d over t, the distance divided by the time, which is 1 divided by 0.0033 seconds. And that will give us a speed of 330 meters per second here. So during the course of this video, we've found that the speed of sound in air is around 340 meters per second. The speed of light in air is much faster, at 3 times 10 to the power of 8 meters per second. Some everyday examples that demonstrate that the speed of light is faster than the speed of sound. For example, lightning storms or fireworks. We've seen how to use d equals v times t to solve some simple wave problems. And you should by now have an understanding of how to measure the speed of sound experimentally. Thanks for watching. Feel free to subscribe and like, and I'll see you next time. Bye.